Ever wonder what a roaring fire, a melting ice cube, and the engine in your car all have in common? Well, it turns out they're all playing by the same set of rules. Today, we're going to dive in and decode the language of thermodynamics, the science that really explains how our physical world works.
So let's start with a little riddle. What do a thermometer and a tire gauge actually have in common? I know, it seems like a weird question, right? But the secret that makes them both work is exactly the same. The fundamental principles of thermodynamics we're about to unpack.
Before we can get to the really cool stuff, we need to learn the language. So this first section is all about getting the basic toolkit down. These are the concepts we'll use to describe, well, pretty much everything in the universe, from a single drop of water to a giant star. First up, mass. And right away, let's be clear. This is not the same as weight. Mass is just a measure of how much stuff an object is made of. Your weight changes if you go to the moon, but your mass, the amount of stuff you're made of, stays exactly the same. We usually measure it in kilograms or grams. Okay, next up is volume. If mass is how much stuff, then volume is simply how much space that stuff takes up. You can think of it as the size of the box you'd need to put something in. And for that, we use units like liters or cubic meters. Now, this is where it gets interesting. Let's combine those two ideas. When we do, we get density, which is all about how tightly packed that stuff is. Think about it. A pound of feathers and a pound of lead have the exact same mass, right? But their volumes are totally different. That lead is way, way denser because all its mass is crammed into a tiny little space. So, here's a quick cheat sheet for you. These are the standard units you'll see for mass, volume, and density. Getting comfortable with these is really the key that's going to unlock everything else we're about to talk about.
All right, we've described our objects. Now let's talk about what happens when we start acting on them. We're shifting gears from just describing things to talking about a dynamic force, the push of pressure.
Here's the thing about pressure. It isn't just about how hard you push. It's about how focused that push is. As you can see from the formula, pressure is the force divided by the area it's applied to. And this simple little equation has some surprisingly big consequences. This is the perfect way to think about it. Imagine you're walking in the snow. Your weight, that's the force, is the same whether you're wearing stilettos or snowshoes, right? But that tiny little area of a stiletto heel concentrates all your force into one high pressure point that sinks right into the snow. The snowshoe, on the other hand, spreads that exact same force out over a huge area, creating low pressure that lets you float right on top. It's the same reason a sharp knife cuts so well. It's all about concentrating the force. You know, just like money has dollars and euros and yen, pressure has a bunch of different units. The official scientific one is the Pascal. But you'll hear weather forecasters talk about pressure in bars, and doctors sometimes use millimeters of mercury. They're all just different ways of measuring the exact same push. Okay, so we've defined our objects and the forces acting on them. Now let's look inside them and talk about their energy. We're moving on to temperature, and we're about to find out what the feeling of hot or cold really means on a microscopic level. This is absolutely fascinating. When you feel that a cup of coffee is hot, what your nerves are actually detecting is the wild vibration of all its molecules. See, temperature isn't really a thing an object has. It's a measure of what its tiny particles are doing. The more they jiggle and bounce around, the higher the temperature. Of course, we have a few different scales to measure all this molecular motion. Most of the world uses Celsius. The US famously sticks with Fahrenheit, but scientists, they almost always prefer Kelvin. And for a good reason. The Kelvin scale starts at absolute zero, the theoretical point where all that molecular jiggling completely stops. Okay, this is it. We've got our toolkit: mass, volume, pressure, and temperature. Now we're ready to put them all together to understand one of the most fundamental rules of the entire universe. It's so important, in fact, they actually had to go back and call it the zeroth law of thermodynamics. You already know how this works. You've seen it a million times. If you put a hot object next to a cold one, what happens? Well, energy, in the form of heat, always flows from the hotter thing to the colder thing. And it keeps doing that until they balance out and reach the exact same temperature. When that happens, we say they're in thermal equilibrium. Now, let's turn this into a really simple piece of logic. Imagine we've got three objects, A, B, and C. So, step one, if A and B are at the same temperature, and it turns out that A is also at the same temperature as C, then what has to be true? Well, it's inevitable, right?
B and C must be at the same temperature as each other. It's that simple property you probably learned in math class. And that elegant, almost obvious bit of logic, well, that's it. That is the zeroth law of thermodynamics. It seems so simple, but it's actually really profound because it's the law that establishes temperature as a consistent, reliable, and measurable property of our universe.
So what's the big deal? Why is this zeroth law so important? Well, it boils down to one thing. It's the reason thermometers work. Think about it. The thermometer is body A, it touches your forehead, body B, and they reach equilibrium. Then you can use that same thermometer to measure a cup of water, body C. The thermometer is the middleman that proves your forehead and the water are at different temperatures without them ever having to touch. So let's just take a step back and see what we've done. We started with the simple language of mass and volume, we built up to the forces of pressure and the energy of temperature, and we ended up at a universal law that makes measurement itself even possible.
We've built a really solid foundation here. But remember, this was named the zeroth law because scientists realized it was even more fundamental than the laws that came before it. And that leaves us with one final, very cool question. If this is just the beginning, what incredible mysteries about energy, work, and the very direction of time itself do the first, second, and third laws have in store for us?